all. This is recording 5, class 5 for mathematics 2621 probability for application class. In today's class, we will discuss random variables and probability mass function concepts. So before starting the class, I have one announcement. So today is Friday, so your homework 1 is going to due today. So homework 1 is going to due today at 11:59 p.m. so in midnight. Okay, so please complete your homework by today. So if you have any question on your homework, please let me know, but don't wait until the last minute. Okay, so the homework going to be logged at after 12:59 p.m. so don't wait until the last minute. Let me know if you have any question, and please complete the homework before it's due time. Okay, so let's start the class. Okay, so we are going to define most important concepts in this course now. So far we learned what is the sample space, what is the event, and some rules related with probability, and some properties related with probability laws. And in last class, we learned conditional and independent probability. So now today we are going to learn some powerful concept called random variable and probability mass function. So before starting the complete definition, a mathematical definition, let's see what is why we need random variable. Okay. So the random variable are something like we are going to assign numerical values for an random experiment outcome. Okay, so seeing things like this, suppose we are tossing 2 coins at once. Okay, so suppose we are tossing 2 coins. So tossing 2 coins. So then your sample space will be head, 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 tail, tail, head, and tail, tail. Now we can define event. So far that's what we did. So we can define event A call has so let's define A, which is getting at least 1 hit. So this means A equal at least 1 hit. So this means it can have more than 1 hit as well. Okay, so these are the outcomes for A. Now, instead of defining event like this, A, I can use a random variable like this. So I'm saying random variable, I'm going to take X is a random variable which number of, I'm going to define X has 1 or more hits. So then X will take some limited number of values. So X will take, in this case, X will take 2, 1, 1. So possible values for X are 2, 1, 1. So instead of defining a set, we can do the same thing using a random variable. Okay. Okay. So now let's see what this slide says. You can think of random variable as a numerical measurement assigning to each outcome of a random experiment. So it's something like this. So the idea of this one here. So we can say X, if you plug X HH, this will assign to 2, and X HT and X TH. Both are so this X is like a function, it assigning values from a sample space or the random experiment to a real number. So this is another example to understand this one, the real world example. If you bet 100 on a red in a spinning of a wheel, the outcome of the random experiment, the spinning of the wheel, is one of red, black, and neutral. So these are the possible outcomes you can have in the in this wheel. So, but you are probably more interested in X. Okay. So the amount of you gain. So X is the amount you gain. So you will get 100 if you get red. If you get black or neutral, you will lose 100. Okay. So that means here X is a random variable and possible values for X are 100 and minus 100. Okay. So that's the idea of a random variable, and this is the definition of random variable. So given a sample space omega, a random variable X is a function that assign to each outcome of omega in large omega to a real number X of omega. Okay. So that's the definition, but you don't want to memorize definition in this class. If you have the idea, that's more than enough. So I can define X as a function from omega, large uppercase omega, to real number line. So you know this notation now, real number line. So it is like we have omega here, and inside omega we have little omegas. And so on. And in this side, we have a real number line. Okay, so it can have different values. It cannot be -3 here, so it should be 0, 1, 2, 3. So now this is like this X, what X do is here, X mapping these values. Okay, so X, this omega 1 is going to map to -2, for example. Okay, omega 3 is going to map to -1 and like this. Okay, so this function, the mapping is called X. Okay, so here for something like this, X of omega 1 equal -2, and X of omega 3 is mapped to, omega 3 is mapped to 2, X of omega 4 is mapped to -1, and this is same as X of omega 2. Okay, so this is like a mapping. So we are going to take all outcomes in our sample space and map those things into a real number value. So we are going to take numbers. So that means if you have characters in your sample space, still we can show that one using a number. So that's the importance of having a random variable. Okay, so the next note, the note about random variable. A random variable can be a discrete random variable, or it can be a continuous random variable. So the discrete random variable means we have discrete values. Okay, it can be finite discrete values, or it can be countably infinite discrete value. So let's Rx denote the range of X. And random variable also can be continuous if it's take values in an interval. Okay, so we will discuss a few examples here. Random variables are denoted by capital letters. Okay, while their values are denoted by lowercase letters. Okay, so for example, uppercase X denote the random variable and lowercase x is denote the its value. For example, we define X has a number of heads, okay? Number of heads when toss 2 coins. So possible values for X are, X can take 2, 1 or 0, okay? Because we can get 2 heads, 1 heads or 0 heads. So these are like little x. So little x take, if little x equal 2 means the random variable take 2, and these are the like little x. So little x are the values a random variable can take. Okay, so now let's consider few examples for random variable. Okay, so suppose we are tossing 3 coins at once. X is the number of tails in each outcome. So I'm going to write down the sample space first. Okay, so sample space. Now you should be able to write this one because we did this one several times. So this is like our toy example. So that's why I'm always taking this example to understand a concept. Okay, so these are the 8 outcomes, and here now you can see X is the number of okay, so I will draw this one in clear place. That's clear place. So then that's like here, omega. Okay, so now X can take, in this case, X is 0 because X is the number of tails, and here number of tail is 1, here number of tail is 1. So all these 3 cases X takes 1. Okay, all these 3 cases X take 1, and all these 3 cases X take 2, and last one is 3. So X can be either 0, 1 or 2 or 3. So those are the possible values for X. And here what happened here is X of H is mapped to 0, and X of T, X of HTH, and X of THH, all these 3 maps to 1. Okay, so that's the thing happening here. Okay? So that's why it is defined as a random variable. It's assigning numerical values, real values to the sample space. Okay, so the next one is tossing 2 6-sided dice. Okay, so tossing 2 6-sided dice. So that's mean the outcome will be, you will get 36. Okay, so omega will be something like this: 1 1 1 2 1 3, and so on, 1 6, and after that you will start with 2 1 2 2 2 3 up to 2 6, and last one you will start with 6 1 6 2 all the way to 6 6. Okay, so this is the sample space for when you are tossing 6-sided 2 6-sided dice. Then X is the number of sum of 2 numbers. Okay, sum of 2 numbers. So sum of two number here will be 2. Okay, here will be 3. Here will be 4, and likewise the last one you will get 12. So the lowest value you will get 2, the largest value you will get 12, and you will get everything between 2 and 12. So here 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So these are the possible values for x. And here, in this case, this is a discrete random variable. So this is discrete. And this is also discrete because we can count. Okay. And this is finite. And this also, second example also finite. First example and second example both are discrete and finite random variables. Okay, so let's discuss the third example. So the third example is rolling a die until 3 appear. So we are rolling a die until we see 3. So here I'm going to take, if you get 3, it's okay. And F means you are getting other than 3. Okay. So F means not getting 3. So that means you are getting 0, 1, 2, 3, 5, 6. Okay. Okay. So that means if you toss it once and if you get 3, you are done. So that's why you have 3 first here. And if you tossed one time and if you not get 3, so that's why it's failed. And then you get the 3 in the second trial. So if you get 3 in the third trial, means you failed 2 times. And if you get 3 in fourth trial, means you fail 3 times. Okay, so that's how the sample space for this example, when you are getting 3, when you are rolling a die until you get 3. So X here defined as a number of trials. Okay, so the number of rolls. So in this case, number of roll in the first outcome is 1, second outcome is 2, here 3, 4, and so on. So in this case, the possible values are 1, 2, 3, 4, 5, 6, and this is going to be continue until to the infinity. So that means this is an example for countably infinite discrete random variable. So this is the abbreviation for random variable. Okay, so this is a discrete countable infinite random variable. Okay. Okay, so the last example, let t be the length of time it takes a truck driver to go from Worcester to Boston. Okay, so truck driver goes from Worcester to Boston. So it is we are measuring a time. Okay, so in this case, this x going to be a okay, so it is not x. First of all, it is not x. Here it should be t. Okay, because it is a random variable is t. So let's correct that one first. Okay, so t. So in this case, the possible values for t will be something between 2 values. Okay, because we can say the lower limit and upper limit for this time, but until we do the experiment, until the driver drive from Worcester to Boston, we cannot exactly say what is the time he will take from this drive. Okay, so let's say this is between 30 minutes to 120 minutes. I'm thinking it's not going to be take more than 2 hours and it should be less than half an hour. Okay, so it's definitely not half an hour. It should be around 50 minutes. Okay, so let's take it, for example, it's between 30 and 120 minutes. So in this case, this is a good example for continuous random variable. So this is in minutes. And this is continuous variable. When it is continuous random variable, we don't say it is countable or countable infinite or finite. So always finite, because we don't know how many values we can take between 30 to 120. Okay, so it is always infinite. So it is it is continuous random variable for the last example. So we did 4 examples, and first 2 examples are like similar. It is discrete and finite random variable. Third example, it is countable infinite random discrete random variable. Fourth one, it is continuous random variable. Okay, so we will discuss both kind of random variables in this class. Okay, hopefully that makes sense so far. And if you have any questions, always I'm happy to answer your questions. You can always visit to my office hours or send me an email. Okay, so now the second topic of this class, in this lecture today, we will discuss is probability mass function. Okay, another important concept. Okay, so probability distribution of a discrete random variable is called a probability mass function, but I know it's not does not make much sense. Okay. Okay, so first of all, let's see how we can define probability mass. Okay, so let's understand what is the probability mass function first, and then see how we can define it. Okay, so suppose you are tossing a coin 2 times. Okay, so I'm always taking this example because it has 4 outcomes. Okay, so this is tossing a coin 2 times. And I'm defining x as number of tails. Here x can be take as x only takes first case 0, and second and third one is 1, and last one is 2. Can we find the probability of getting 0? So can we find this one, probability of x getting 0? So that's mean probability of getting x equals 0 is same as probability of x, probability of getting head. Okay, this is same as probability of getting head, because we will get x equals 0 only when the outcome of HH occurred. Okay? So this is the probability of getting HH is 1/4 if this is a equally likely event. And similarly, we can find the probability of getting x equal 1. So x equal 1 will take in 2 cases. So it is 2 out of 4. And probability of x equal 2 is again 1/4. Okay. So these probabilities are the probability mass function of this x. Okay, so these probabilities are the probability mass function of x. So when x equals 0, we have 1/4. When x equal 1, we have 2/4. When x equal 2, we have again 1/4. So these 3 values are the probability mass function values for this particular example and this particular x. Okay, so this now we can define and denote the probability mass function, and here probability mass function also can be abbreviated as PMF, probability mass function, PMF. And probability mass function is used for discrete random variable. So we say probability mass function for discrete random variable. Okay, it's defined here. Okay, so it's discrete random variable. And there's a different name for probability function when we have continuous random variable. We will learn that one later. So for now, for the probability distribution function for the discrete random variable is called probability mass function. And we can define it in, so it has different alternative ways. First one is px, little x, okay? Or we can say p larger x, uppercase x. So this is the random variable. Take some any x value, little x value. So this is same as this is a definition of probability mass function. So probability of taking outcome. So this is the outcome of our random experiment. Outcome of random experiment in omega such that so this is such that x of omega equal x. This map equals to x. So that means take the probability where omega inside the sample space such that this map equals to x. Okay. Okay. So, but you don't want to memorize definitions. I'm very. It's very important to know understand the idea. That's more than enough. Okay. So now the properties of probability mass function. That's very interesting. It has very interesting 3 properties. First property is all probability values should be between 0 and 1. Okay, so you cannot get probabilities for any x value above 1 or less than 0. And if you take the summation of all probabilities, you should get 1. Okay, so here, for example, here if you take 1/4 plus 2/4 and 1/4, so you will get 1. Okay, you will get 4/4, which is 1. Okay, so that's the idea of the second one. Okay, so if you take the summation of all probability values in the probability mass function, you should get 1. And all probabilities must be between 0 and 1. And the last one is important to find the probabilities using a probability mass function. Okay, so the idea is if you want to find the probability of a subset of A, okay, so what you can do is you can add those probabilities in that subsets. For example, for our previous example here, suppose you need to find the probability of x. X means the random variable is less than 1. Okay, so that's mean you have to do is you have to find probability of x equal 0 plus probability of x equal 1. So probability of x equal 0 is 1/4 plus probability of x equal 1 is 2/4. Altogether it is 3/4. So this is the example of, yeah, we write down the example. I will refer the example here, example of tossing 2 coins. Okay. And this means getting at most 1 tail. Okay, so this is the event here. Okay, so this is the event, getting tail at most 1 tail. Okay, getting at most 1 tail is this event we can denote by x less than or equal 1, and we can find the probability by adding x equals 0 and x equal 1. So that's the last point means. Okay, now let's do 2 examples. Okay. Okay, so first example, tossing a coin 3 times, and we are going to write down the probability mass function of random variable when x exceeds the number of heads now. Okay, so first write down the sample space. So this is sample space when you tossing a coin 3 times. Now let's define x is the number of heads, Now X take values like this. X take, I will write down the values here. Write the values here. X is the here X is 3, here X is 2, 2, 2, here 1, 1, 1, and 0. So these are the possible values for X. Okay. Okay, so now let's calculate the probabilities. So now let's calculate the probability of X taking 3. Okay, so when X is taking 3 is same as probability of head, head, head. By assuming these are the fair coin, we can calculate the probability of getting head, 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 which is 1/8. So there are 8 outcomes in n omega. Okay, n omega is 8. So it is 1/8. And similarly, calculate probability of X equal 2. So X equal 2 will give you in 3 outcomes. So it is probability of HT plus probability of HTH plus probability of THH. So this means 3/8. So 1/8 plus 1/8 plus 1/8, you will get 3/8. Now let's find probability of X equal 1, which is you will get probability of HTT plus probability of THT plus probability of TTH, which is again 3/8. Last one, probability of X equal, I will write down here, probability of X equal 0. There's only one case, TTT. Okay. Which is 1/8. So there's only one case when you take X equal 0, 3 cases for X equal 2, 3 cases for X equal 1. Now when we are denoting probability mass function, we can use 2 methods. First method is use a table, denote all possible values for X. So 0, 1, 2, 3. And here probability of X equal little x, the second column, second row, and write down the corresponding probability. Here it is 1/8. This is 3/8, 3/8, and last one again 1/8. So this is the probability mass function of X. So this is the PMF of X. Okay, so there's another way, which is using a stepwise function form. So we can write probability of X. I will use different color here. Okay, so this is the second form. So you are feel free to use any method you like. So the second one, probability of X equal little x. We are going to use stepwise function form. So there are 3 values. So you can write like this: 1/8, 3/8. Okay. So it is it will take 1/8 when X equal 0 or X equal 3. It takes 3/8 when X equal 2 or X equal 1 or 2. Okay. So X equal 1 or X equal 2. Okay, so this is another method to write down the probability mass function of X in this example. Okay, so you can use either method. I prefer to use this one. That's very easy. But you can use this one as well. But it is up to you. You can use either method. Okay, so hopefully that makes sense. Now, the last example, which is something related to the real world. Okay. It's not a technical example. Among a sample of 50 families, 10 families had 2 members, 13 families had 3 members, 21 families had 4 members, and rest of the families has 5 members. Okay, so X is the number of members in the family. Find the probability mass function of X. Okay, now in this case, we can start with write down the possible values for X. So the possible values for X are, can get 2 members, 3 members, 4 members, or 5 members. So these are the possible values for X, because X is the number of members in the family. So it can be 2 members, 3 members, 4 members, or 5 members. So in this case, this is a finite discrete random variable. Now we have to find the probabilities for each case. Now let's calculate probabilities one by one. Probability of X equal to, which is having 2 members. So 10 families has 2 members, so it should be 10 out of 50, which is 1/5. And let's find probability of X equal 3, which is having 3 members. It is 13 out of 50. Okay, so I will, so we cannot break this one further. So the last one, one before the last one, X equal 4, which is 21 out of 50. And the last one, X equal 5, which is the rest of the family. 10, 23, 21. So it is all together, I think 44. Okay, so let's see. 23 plus 21, which is 44, 6. Okay, so the rest of the family are 6. So 6 out of 50. So that means 3 over 25. So these are the corresponding probabilities when X take 2, 3, 4, 5. Now we can write down the probability mass function in any of the method I have explained in the previous slide. So I'm going to denote this one using first using the table. X take 2, 3, 4, 5, and probability of X equal little x, which is when it is 2, 1/5. When it is 3, okay, so here 1/5. When it is 3, 13 over 50, 4, 21 over 50, 5, 3 over 25. Okay, so this is the table. So it's better to have the lines as well. And second method, using stepwise function. Okay, X equal little x. So in this case, we have to list all 4 waves. 1 over 5, 13 over 50, 21 over 50, and last one, 3 over 25. And in this probability will give you when X equal 2, this is X equal 3, this is X equal 4, and this is X equal 5. Okay, so this is the second method. And it is always better to check your probability values is add up to 1 or not. So it is 1 over 5 plus 13 over 50 plus 21 over 50 plus 3 over 25. So let's see, this is add up to 1 or not. Okay, so it should be, but it's better to check always. It is going to give you 1 or not. So use your calculator always. That's easy, and don't input garbage to calculator. So then you will the output will be the garbage as well. So be careful when entering numbers, and practice when you are doing homeworks. Please practice to use your calculator. Yes, this will be 1. So that's true. So can you see all probabilities are between 0 and 1, and it is if you add all the probabilities you will get 1. So all first 2 properties will be satisfied. And the last part of the question, compute the probability that a family has 3 or more members. So, and this is a very important part. So when you see a question like this, okay, so you have to convert this question into in terms of random variable and probability notation. So here, can you see? This is asking your X, the random variable, because random variable is the number of members in the family. So X is 3 or more. So that's mean it is asking to find this probability. Okay, get the idea? So it is asked to find this probability. Convert this set of words, so this part. So this set of words into the probability notation. So here the question directly asks what is the probability of X equal 3 plus probability of X equal 4 plus probability of X equal 5. Okay. So in other words, here this is asking X take 3, 4, 5. X can take 3 or 5. So that's those are the values question asks, because it's asking family members has, it's asking family members has 3 or more members. So 3 or more is 3, 4, 5. So X can take 3, 4, 5. So when you have to add the probabilities when X equal 3, X equal 4, and X equal 5. Now you can use your table. So when X equal 3, you have 13 over 50 plus X equal 4, you have 21 over 50. And when X equal 5, you have 3 over 25. So find this answer. So you should get 4 over 5 or 0.8. So both answers are acceptable. Okay. And one more thing, you can do this one in the another method. Okay. So I will, it's better to discuss that one here as well. So this is method 1. And there's another method to do this one. Okay. So the same explanation. So the question asks to find X greater than or equal 3. So it is asking X above 3 or more. Okay. So your X takes 2, 3, 4, 5. Okay. So the question asks to find 3 or more. So the question asks to find probability from here to above. So what you can do is, I can do something like this. So this is very important concept. We will use more in later part of this course. So we can do 1 minus. So because if you add all the probabilities, you will get 1. So what I'm going to do is I'm going to take 1 minus this probability. 1 minus the probability when X equal 2. So then I will get the probability of 3, 4, 5. Okay, so here 1 minus probability of X equal 2 is 1 over 5. So now you will see, you will get the same answer. Okay.